Well, again, I think it's important we start talking about lightning protection and how to work or use or integrate a lightning protection technology. You got to start at the beginning, which is the actual lightning storm, electrical storm itself. The first few slides here, we kind of laid a foundation about some of the basic principles. I'm talking a little bit about, ionization. Well, I've last few years, I threw a couple slides in there just to kind of give a little example about what ionization is. Because a lot of times we talk about our devices as ionizers, our lightning protection systems, excuse me, whether they be a dissipation array system, or whether they be a spline ball terminal system, or spline ball ionizer, as a ionizer. So I kind of have a couple slides to talk briefly about that. And actually, let's start with the electrical storm formation. This is kind of a consensus of the scientific community of what actually creates an electrical storm. What's the recipe? What's the motivation? What are the factors that create a scenario in which we can have an electrical storm? Well, these are kind of the bullets, if you will, the ingredients in that recipe. So first of all, we're going to have a storm cell developing here. We have a rain cloud. Say it could be a rain cloud to start with. We're going to have moisture in it, so we have water droplets inside the cloud. We have moisture. We have wind. Now, I did a lot of traveling years ago, not as much as I used to, but I've done a lot of travel in aircraft, and in my territory that I was doing all my sales work in, a good portion of that territory was the Midwest or the Gulf Coast. Well, in the springtime, summertime, if I was flying into Houston, for example, and it was the right time of year, maybe the springtime, April, May, maybe in late summer, I'd always have to kind of watch the weather because that's a perfect time of year for lightning. Well, as you kind of fly in that environment in an aircraft, one thing you notice if you're on a thunderstorm is chop. We call it chop, turbulence, a lot of wind dynamics going on in the storm. So in an electrical storm, you have a tremendous amount of wind inside the storm. Updrafts, for example, if you've been in an aircraft and you've hit that pocket of turbulence, sometimes a downdraft, sometimes an updraft. Either way, it's not good, the big ones. Well, that's wind dynamics inside the storm. So you got water, wind. You have temperature variation. A thunder cell can be up to 50,000 feet in elevation. Very rare, but they go that high. Easily 40,000 feet. That's why, again, if you're in an aircraft and you're trying to fly from point A to point B, you can't really go over the thunder cell. Most aircraft top out maybe mid-30s, 35,000 feet-ish is where you're going to be your maximum cruising altitude for a commercial aircraft. Well, if it's 40,000 feet, 45,000 feet in elevation, you're not going to fly over it. You have to fly around it. So obviously, if you're, let's say, 10,000 feet above the Earth's surface, 5,000 feet above the Earth's surface of that cloud, but the top of that cloud is 45,000 feet, from the bottom of that cloud, you might be 50 degrees F. But halfway up that cloud, you're below freezing. And of course, the top of that cloud, you're well below freezing. So we have a tremendous variation in temperatures in that cloud, from below freezing to above freezing. So keep that in mind. Well, how does that impact this whole scenario? Well, you have moisture, you have wind. So let's just say you have some water in the cloud. It's down at the bottom portion of the cell. The wind picks it up in an updraft, hurls it, propagates it up in the cloud. So I go from a below freezing to a freezing scenario. So the temperature changes, that water droplet becomes really a sliver of ice, or even hail. It gains mass, gains weight, and as it gains mass and gains weight, it's up at the top of the cloud. Now all of a sudden it's got weight, gravity takes effect, or wind, and it drops it back through that cell. Again, now we're talking about what could be a significantly large thunder cell. So maybe we're at 40,000 feet, and as we plummet back down through that cloud, that hail collides, hits an upward moving, let's say, ice sliver or hail. So it collides. And during that natural collision effect, it collects an electron. So again, we have water, wind, turbulence. We freeze the water, becomes hail, gravity takes effect, it falls through, and as it falls through the cloud towards the Earth, it gets hit with an upward moving, let's say, ice sliver, water droplet, and during that collision effect, that colliding effect, electrons are collected on the bottom portion of the water or hail. More electrons means a negative charge. So we get a negative charged atom by doing so. Some very simple science here. The center of an atom is positive charge. This goes back to our early days. Electrons have a negative charge. Electrons move around the center of the atom. A positive charge of an atom, the positive charge of that atom pulls the electrons close to the center of the atom. Opposite charge attract, and kind of keep us in mind down the road. Pretty simple when you're in the lightning protection business. Opposites attract. It's very true. And that's what creates our lightning event. So here's our little illustration of an atom. Very simple. You got your protons near the center of the atom. You got your neutrons, nuclear charge, your nucleus. And here's our electrons. Now in this case here, if you have an atom that has the same amount of electrons equal to the same amount of protons, it's a neutrally charged atom. There's no positive charge, there's no negative charge. It's neutral. Now when we talk about this particular illustration, they do match. It's a neutrally charged atom. Now an ion, because we talk about ionization and so on, but an ion is an atom or molecule which total number of electrons don't equal the total number of protons. So given either net, negative, positive charge. Why is that? Why are we just talking about this? Well, I'd like to kind of lay the foundation for charge separation, what creates the charge. Remember I talked about in the second slide that as that hail plummets back down through the cloud, we collide and it collects an electron. It grabbed an electron from the associated atom. That means that atom that grabbed that electron most likely now has a negative charge if it has more electrons. The atom that lost an electron, gave up an electron, is now positive charged. And that one goes to the top of the cell, and the negative one to the bottom of the cell, typically. Again, more electrons than protons give you that separation of charge. Now what we're talking about here, we talk about ionization a little bit, is ionization basically is the physical process of converting an atom to an ion by adding or removing a charged particle like an electron. So when we talk about what we're doing, we're basically allowing electron flow, charge flow. Actually allowing electron flow to an area that doesn't have enough electrons to one that has too many to neutralize that charge. We're allowing electron flow to neutralize charge to some atoms that don't have enough. We allow them to flow to that atom and thereby reduce that electrical charge, that particle. And we'll talk about that in a minute, well, or in a few minutes. Excuse me. Now we have a number of new slides that we have, excuse me. We have a number of new slides that we've put in this presentation. Some of them are going to be actually kind of redundant. The reason I wanted to put a couple of redundant slides in there is because I think the visual aid, showing it a different way, helps you maybe understand the principle and the idea we're trying to present. So now we're showing you a mature electrical storm. What we mean by that is, remember the first few slides we showed you that we have an electrical storm forming. We had the wind, the gravity, charge, we have the temperature variation, we have hail, collision effect. So now this has already happened. We already have that recipe happening. So we have a dynamo. Dynamo is our cloud. We already have charge separation. We have positive potential clustered at the upper portion of the thunder cell, and we have negative potential down here. Why is it negative here? Those atoms have more electrons. These atoms up here, less electrons. Positive charge, negative charge. The force and magnitude of that negative potential on the base of the thunder cell forces a positive charge on the Earth and Earth-bound structures. So that negative charge on the bottom of that cell is forcing a positive charge. We can almost call it an electrostatic shadow on the Earth and the Earth-bound structures. Now, we've kind of given you some nice even lines of visual indication where we're saying, okay, here's my cloud. Here's this little electrostatic field shadow. What we're saying here is that if we look at the charge in the air, there's always a charge in the air. Even today, if I was to walk outside and measure a 1 meter air gap with an electrostatic voltmeter, so I was to go outside and measure air gap about 1 meter with a voltmeter that could measure electrostatic field potential, I would have at least, if I was going to have a lightning storm or I could have a lightning strike occur, the minimum threshold that the scientific community has established is I have to have at least 5,000 volts per meter of charge in the air. Could be as high as 30,000 volts, 30 kV. So kind of your spectrum of the electrostatic field intensity that you're going to get during an electrical storm has to be at least 5,000 volts a meter, or could be as high as 30,000 volts per meter. And that's what we're showing you in this little gray area here. This is the Earth's surface. That's the bottom of the cell. And in this area here, we have some significantly high charged air, charged by the storm itself, created by the storm itself. Now, why is that important? There's two reasons why I want to kind of keep that mental note. One is because as this field potential grows, that leads to a lightning strike. And we'll talk about that in a minute. But secondly, to make our lightning dissipation systems work, they use that high charge in the air really as a power supply, almost to its benefit. That's what we use to make our systems work, that high electrostatic field. Our systems are a passive system. On occasion we get asked, well, is there a magic black box? Is there a power supply? You know, is it an active system? In electrical terms, if you had any electronic courses or engineering courses in power, they talk about passive systems and active systems. Passive mean basically it doesn't do anything, it sits there doing nothing, it's grounded, let's say. An active system might have a power supply, be plugged into the wall, have batteries, maybe a photocells, but it has constant, constant internally generated power. Well, this is basically a passive system, except what makes it active, that's our power supply. So again, now we're showing you the charged cell, positive, negative, forcing that positive charge on the Earth. As that storm cell moves across the Earth's surface, that positive charge flows with that thunder cell. Now, if I was to measure from the Earth to the bottom of that thunder cell, that cloud, with a voltmeter, an electrostatic voltmeter, we're in the area of around 10 to the 8th volts potential, plus or minus 10%. You're in that area spectrum of voltage, so 10 to the 7th, 10 to the 8th, 10 to the 9th. So we got a tremendous amount of difference of potential between the Earth and the cloud. Now, what I have done here is I've just zoomed in. Here you have if you're out there in a plant and you're out, maybe a mile away, you see the plant in the horizon, it's all by itself. You see this a lot maybe with utility nuclear power plants that are always by themselves. Maybe it's a small refinery out by itself. So you're driving up to the property, it kind of looks like this. Now we're on the property site. We've walked on site, so now we're standing on the property, and now we're taking a little closer look at what I just showed you, that's all. Here's my positive charge. Obviously, as I get closer, excuse me, you got your negative charge here on the base of the cloud, positive charge at the top of the cloud, but now we're kind of zooming in into the shadow. So now we expanded the shadow. In this area here, we have that very high electrostatic field developed. Now everything in this area here, obviously, is vulnerable to a lightning strike. We could have a lightning strike to the stacks, to the vessel, process vessel, maybe the control room or the office building here, maybe some remote I/O buildings or labs, maybe your transmission line, maybe your communication tower. Even these trees, obviously, even a blade of grass is all in the area which could be susceptible to a lightning strike. Again, I threw another slide in here. I'm kind of being redundant, but I want to kind of get this whole visual understanding across. Here is my shadow. This is the electrostatic shadow. Obviously, the shadow goes all the way across these process vessels, also goes across these tanks. They're all going to be immersed in a high electrostatic shadow. They're taking on that charge. They're immersed in it. So now, what's happened? Let me back up 1 second here. So when we go back to the slide, we talked about the very high difference of potential, voltage potential between the Earth and the cloud. Now, in one of my previous slides, we talked about opposites attract, right? Negative and positive want to short out. So we see this negative here, we see this positive here. What is stopping that negative and positive from shorting out, coming together? Why aren't we just having a discharge, you know, even in maybe with about 500 volts per meter? What's stopping that discharge process? Well, well, may not be the obvious answer to a lot of you, but the straightforward, easy answer is air. Air is a natural dielectric. It's a natural insulator. Air itself provides the mechanism, the buffer, between those two charges so they can't short out. It's like a piece of rubber in here, for lack of a better term. It's like putting a piece of rubber in here that says you guys can't come together. But it has a dielectric rating, an insulative rating. It varies on its rating of insulation capabilities, but as that potential, as that difference of potential becomes so dramatic, so great, as we mentioned, it could be anywhere from 10 to the 7th, 10 with 7 zeros, 10 with 8 zeros, basically 100 million volts or what have you, or greater, that air can no longer work as an insulator. It no longer says, I can stop you from conducting. So the air actually becomes a conductor. It allows conduction. You break down the insulated capability of the air, and now we have a spark developed. In fact, in certain scientific terms, some of these scientists who actually analyze, evaluate, test lightning, they like to refer to this as a long spark. In one essence, it is a long spark. Similar to like if you're in a dry, static environment and you're walking on a carpet and you reach for a doorknob and you get a spark. Similar, except a lot more energy behind that long spark. Now remember I talked about the 10 to the 8 volts? So there's an illustration of 10 to the 8 volts plus or minus 10%. So now we have had this high charge in the air. So kind of walking through this slowly, we have a situation when we had a storm develop, we had all the right components, we had wind, moisture, temperature variation, collision effect, charge separation, developing as high charge separation. Now the air can no longer work as an insulator, and I have a lightning bolt developed. Now, this lightning bolt, we've frozen it in time, but it is, in simple terms, is a conductive ionized path. Again, trying to keep things simple in my descriptions, I like to refer to that as like a conductor, like a wire coming down from the cloud. It's like you're bringing a wire, a bare piece of wire, copper wire, coming down from the cloud. So that means that if I had 10 to the 8 volts, for this example, let's just use 10 to the 8 volts potential between the cloud and the earth pre-lightning strike. As I bring that leader down, I'm bringing with the tip of that leader, that lightning bolt, that high potential. There's a small voltage drop across this, pretty minimal. As I bring that leader down and bring that high potential with it, what happens? If my air gap, let's say initially, was, let's just say 10,000 feet from the earth to the cloud. Now that leader's coming down 9,000, 8,000 feet, 7,000 feet, 6,000 feet, 5,000, so on and so forth. Obviously happening less than a second. But as that comes down, what has to happen? If I have the same 10 to the 8th potential, but now I'm just say a few hundred meters away from the earth, 100 yards from the earth, what has to happen? If my field intensity is this pre-lightning strike, and now my air gap is now only a couple hundred meters, now I've frozen in time, I've stopped the lightning bolt, so I can kind of give you a slow description here. The electrostatic fields between the tip of that leader, that lightning bolt, the end of that lightning bolt, and the earth or earthbound structures has to increase. Same potential, smaller air gap, kilovolts per meter have to increase because my air gap's less. So as I bring that voltage leader down, that 10 to the 8 volts, and I come down from 10,000 feet, 9,000, so on, pretty soon I'm close to the Earth. But I have a very small air gap now, which means the kilovolt per meter in the air, that electrostatic field increases. Why is that important? Because in the vicinity of that lightning bolt, upward streamers will be developed from earthbound structures. So now all of a sudden we have all these upward streamers. In this case here we're showing a blade of grass, we're showing a tower, we're showing a processed vessel, maybe a stack. Everything in the air is generating a streamer in the area of influence. One of these streamers will win the collection race. And now we've determined point of collection. So on occasion we get asked a question, I'll be in an engineering presentation, and I'll have somebody ask me a question, hey, I heard lightning comes from the ground up. Well, the answer is yes, you can get ground generated leaders and lightning. In fact, to get upward generated lightning, though, you have to be about 100 meters in elevation. In other words, it's extremely rare and probably not going to happen to get an upward generated lightning leader, not a streamer, from the Earth, unless you're like a tower. This tower might be 100 meters tall, maybe it could generate it. And you might be sitting in the horizon and see that tower in the distance and generate a leader going up from the Earth. Very rare, possible, but it has to be typically over 100 meters tall, 300 feet tall. Again, that's pretty rare. But what we do have for sure is the point of determination of what's going to be hit, what's going to be collecting the strike, is generated from the Earth up. So what we do know is that these are called streamers, not leaders. These are in this scenario here, this example I'm using, these are referred to as streamers, not leaders. These upward streamers are, one of these will actually determine point of collection. So as far as determining what's going to get hit, it is generated from the ground up. Do you follow me? This is kind of an arbitrary path from the cloud to the Earth. But once it's close to the Earth, what's going to determine collection is driven from the Earth side. Why is that important? All the standards that we use today as far as lightning protection, the most accepted standards that we see throughout the world, whether it be in the United States or in Europe or in other parts of the world, I mean, they're almost all the same with some slight modification, deviation, is ensuring to develop a very competitive upward streamer. All this, for a lightning rod system, we'll talk about that in a minute, its whole mission is to be a competitive streamer generator. It wants to be the preferred collection point, using the facts that we know about lightning. For example, here's an example of one of the standards. If we look at NFPA 780, and we look at some of its strike zones, and there may be some debate about the strike zone being correct or not, but their premise on that particular standard is, I've got my lightning bolt coming down in an arbitrary fashion. Here's my downward step leader. It reaches a point of discrimination. It creates a strike zone. This strike zone basically is an envelope that says that that streamer that's going to collect that lightning bolt will only be developed from inside that strike zone. So if we looked at this example and kind of froze in time, we're saying, okay, here's a downward step leader. We've reached a point of, in our mind, point of discrimination. Now we're saying, okay, anything inside the strike zone will develop that streamer that may collect it. And the standards now say, I want to make sure I have a lightning rod in that area to collect it in a preferred grounding path. Now again, one of the things we want to make sure we understand here is that these are all collection ideas. Problem with the collection approach is, yeah, you got that lightning strike, you've collected it, but now the downside is you have collected it, and now you've got to deal with it. So that's where we kind of take the inverse approach than that. So I like this slide, this particular example here. Hopefully it'll give you a good idea of a slow motion lightning strike. The reason I like this particular video, and I'll play it a couple times, is because it gives you a lot of examples of what we talk about in our presentation and how our system works down the road. So I'll play this again in a second here. Let me go back if I can. So look how many branches to that main tree, how many twigs, if you will, are on that main leader. It had a large envelope, a large area in which that lightning bolt could be collected. You can see we're talking about maybe, in this particular case, maybe was it going to be collected over here? Was it going to be collected over here? In this case, that streamer on that branch won the race. That's where the point determination was. Also, what I like about this particular video, and I'll back it up one more time, and that'll be the last time to play it. You can also see a little bit of the what's called return stroke and dart leader. We'll talk about it. There's your return stroke right there. Everything is dumped down that main channel, and that right there is the dart leader return stroke, where you have another surge of current being dumped down that closed ionized path, down that closed circuit, if you will. Typically, there's not just one surge of current in a lightning strike. There's multiple surges of current. And that's basically going back to what's called the dart leader return stroke. And the best way to describe that is when you see a lightning strike on the horizon and it looks like it's flickering on and off, the lightning bolt's not changed its look, its configuration, but it seems like somebody's turning a switch on and off. That's different. We call dart leaders and return strokes all happening in one closed lightning discharge, equating to different surges of current. Not that it really matters much, but it just gives you an idea of what that causes that flickering effect. Here's an example of, yes, you can see that this one large lightning strike, which had a large area of potential collection, had multiple upward streamers all developed off that one lightning strike. Now, these did not win the race. They didn't collect, obviously. The one that did win the race is the one you can't see. It's the one that closed that, I like to describe it as closed that electrical circuit. We've made that electrical circuit closed, now we're having that major current flow. I kind of just talked briefly about, what's in a lightning strike, because sometimes you might have somebody ask you, well, what's a dart leader return stroke? Well, that basically, we showed you on that video that here's our lightning strike, here's our branches. One is we'll collect. That's the return stroke. Dart leader comes in right here where you fill that channel again, dart leader and return stroke right there. And that's basically what we're talking about, is kind of multiple rushes of current that are basically in the vicinity of that closed channel in the cloud, get funneled down that closed channel. Lightning strikes well over within about a second, but it might have multiple discharges in that one closed channel. Now, the real issue here is not the actual lightning strike. First of all, there are standards that have been out forever, and they've been very, very good and effective in actually doing their job, collecting lightning strikes. But what we have found is that when you collect a lightning strike, you have all of these byproducts, secondary effects that are caused by that lightning strike. And these secondary effects, reality, from an electronic integrity standpoint, it's these secondary effects that are the real problem. The direct strike really isn't an issue. I mean, lightning rods are great. They do collect, they take it to ground, they minimize structural damage. But it's these secondary effects, and what we haven't really put in here, we should put in here, should add to our presentation, is explosions. What we have seen a lot now in our oil and gas industry in the United States is a lightning strike is a spark. It's a spark. It has temperature, and if we have vapors in an area, explosive vapors, and we put a spark in there that has a high heat coefficient, and we have flammable vapors, we have now created the ignition source for an explosion. And so we're seeing a lot of that, which really should be added to the slide, is potential explosion event, especially in the oil and gas industry where they're venting flammable vapors. But we're going to kind of break this down here. For example, one of the primary problems that we do see on a regular basis is induced voltages on buried cables. If you're using a fiber optic cable, not necessarily an issue. Those are impervious to an induced voltage and current. But in this example here, let's say we have our control room with our DCS in the ground floor of this building here. Maybe it's a Bailey Control, Foxborough, Honeywell, DCS. And we're communicating with some instrumentation controls in the field. And then that communication is done via buried cables in either conduit, raceways, or what have you. Well, remember we talked about the fact you had positive charge on the upper portion of the thunder cell, negative charge on the base of the cell. We're inducing that positive charge on the earth and earth's surface. Those buried cables are immersed, surrounded by that positive charge. So now we have a lightning strike in the vicinity, let's say to this tree, not even to the building itself. What has to happen? Now the earth surface, again, is working like a plate of capacitor, holding that charge. Even though it's a rather poor semiconductor, it does hold that charge. And now that positive charge has to propagate, rush, flow very quickly to the point of termination in microseconds. So as that positive charge flows across the Earth's surface, it induces a voltage transient on those buried cables. And that voltage transient will go both directions, go onto the field side instrument as well as on the control room side. So we can have a scenario where we have an instantaneous failure of our field electronics, or maybe an I/O port, I/O card at our DCS. That's the obvious one to be able, anybody can figure that one out. I had a lightning strike, I heard the thunder, bam, I lost that instrument in the field. Pretty easy to say that was lightning generated failure. The second thing that can happen is a false signal. Now we see that a lot on analog circuits. Analog circuit is very common in the chemical processing, petroleum refining business, as well as other even utility side, where you're running a current loop from the control room side to the field instrument, field transmitter. And it's running at 4 milliamps on a minimum, 20 milliamps on a maximum. An average might be, say, 12 milliamps. At 12 milliamps, everything's fine. But when this voltage spike is reflected, induced on those buried cables, you increase the voltage, you increase the current. That DCS, which says, hey, everything's fine at 12 milliamps, but if I get to 18 milliamps, I got too much pressure, I got too much temperature in that vessel, I better shut down. And we see this on numerous occasions where you'll see a lightning flash, you'll hear the thunder, and automatically the DCS just starts shutting down. Nothing was damaged, but when they go back and they check the report of why the DCS went through its shutdown scenario, because it thought that vessel had too much temperature in it, it might blow up, it was a false signal on that analog circuit that created that trigger that shut down the system. And we'll talk about this a little bit later on, but when you have a shutdown, you have major problems. You can't turn the process right back online. A lot of these processes take about 8 hours to shut down and bring back up. If it's in a refinery scenario, you're flaring the product, so you're burning money, and so you're not producing and you're burning money. And these can easily cost in excess of $250,000 to $1 million per shutdown, caused by a false signal. So this is another secondary effect that is a big problem in the refining industry. Here's another example. Again, as I mentioned, I'm going to throw some slides in there that are redundant, just a little different visual aid. Same idea as this slide. It's an older slide we had, but you can see here's my building, my DCS is in here, my field I/O building, my instrument building. Here's my buried cable, lightning strike to the tree. That positive charge flows to that point of discharge. I induce that voltage, goes both directions, and I got a failure. The same secondary effect of an earth current transient, just give you a little different visual aid of the problem we have. Now, an atmospheric transient is different. It's created by collapsing fields. This is not as significant as a problem as the earth current transient or a direct strike would be to, let's say, a cable tray. But as you might recall, we talked about during a mature electrical storm, there's at least 5,000 volts to 10,000 volts per meter of electrostatic charge in the air. So if I was to measure, again, a meter air gap, and for this example, let's just use 10 kV about an average electrostatic field condition prior to a lightning strike. And if I had an overhead cable tray in here that was 30 feet tall, or a power line or in-plant communication line, and let's say it's about 10 meters tall. 10 meters tall is about 30 feet. So those like English units, 30 feet. Those like metrics, 10 meters, they're about the same. You'd have about 10 kV per meter at 10 meter elevation, about 100,000 volts of electrostatic potential reference to that cable to ground. Now we have a lightning strike in the vicinity. What happens when you have a lightning strike in the vicinity? That electrostatic field collapses as it shorts out. As it collapses, it creates an atmospheric transient. That transient propagates through the air, induces a voltage transient. Here we're showing you on transmission lines. Probably not a good example. Why? Because transmission lines are running at, what, 230 kV, for example. They're not going to care about it. But if that's a low voltage analog circuit, it's a big deal. Transmission line running at 230 kV or 120 kV, no big deal because it's a kilovolt impulse anyways. But if it's a low voltage line, that induces a low energy transient, that can be a problem. For example, in a refining environment, in a power plant, they use a lot of overhead cable trays. That would be an issue where they could induce a voltage on those overhead cables in that cable tray. We do, in general, we're going to talk about grounding design, grounding principles later on. But in general, as a standard design protocol for lightning protection, you want to have common grounding. So if you grab the NFPA 780, National Fire Protection Association 780 standard, it's going to talk about the need for common grounding. They don't talk about ground as far as what type of ground resistance you want for that ground grid. In other words, NFPA 780 doesn't say you need a 5 ohm ground. We kind of say you should have a 5 ohm ground. But they do say you need common grounding. So you don't want to have two different grounds. We'll see this quite often in a chemical plant, power plant environment, where you'll have maybe the DCS because Foxborough or Bailey Controls says, hey, I could have my instrument grade ground and I want it completely isolated because I'm so sensitive, I don't want any noise on there. And then you have the plant ground. So the plant ground can be described basically as R1 and R2 is your DCS ground. So they're totally isolated from each other. They're both ground rods in the earth, but the plant ground is a significant large ground. It's the whole plant ground. It's all tied together. It's structural steel, it's the vessels, it's the foundation, it's the electrical system all tied together. Well, this DCS is out here with 3 8-foot rods in a triad by themselves. They're not tied to the grid. Well, the problem is you have a lightning strike. Let's say a lightning strike hits a stack back here and it dumps an average lightning strike's around 30,000 amps. So 30,000 amps, and if our ground is 5 ohms, we're dumping about 150 kV. Ohm's law says voltage, keeping it simple here. Ohm's law, voltage, E equals I times R. I, 30,000 amps, R, 5 ohms, 150,000 volts on this ground for microseconds. Well, this ground here is still feeling the effect of that current. It's in the same vicinity of that current flow, but it's at a much higher resistance. So it's not tied to this ground. So maybe it's that, maybe this ground over here is 300 kV because it's twice the resistance. Now all of a sudden, they want to equalize each other. So if I've got a resistance between this ground here, which is the earth, and that ground, and I have voltage potential difference, this is at 150 kV, and that's at 300 kV, I got a 150 kV difference of potential between those two grounds. Current's going to flow back and forth. If I got resistance and I got voltage, I'm going to have current flow. Natural principle of electrical discharge. And now these have these currents that flow trying to equalize themselves creates all sorts of havoc with our sensitive electronic systems. Simple solution, tie them together. Make sure all your grounds are bonded together, connected together, at least in the earth. So when you have a lightning strike, they all rise and fall at the same potential. You don't want, and so we constantly see this in the United States where these grounds are tied together. When we do a consulting job, we'll come in and say, listen, if we do see that out on the sites, and I would say probably better than half of the projects I've been involved with have this scenario. We'll go back and say, listen, all you need to do is tie these two grounds together in the earth. You can keep it isolated above ground, but when you get in the earth, make sure they're bonded together. That minimizes any noise, because the earth is a great noise attenuator. The earth itself will attenuate any noise that might be on that ground from your plant. But when you get in the earth, you don't tie those together, you're going to have a problem. We also have a secondary effect called an electromagnetic pulse, EMP. If you look at the base equation, which drives the potential for an electromagnetic pulse, it's basically created by change in current over change in time. Well, if we have a lightning strike current that's high enough, and has a fast enough rise time to that peak current, you can create a significant electromagnetic pulse. Now, most of our lightning strikes probably won't do that. We don't have a bell curve here, but in general, lightning is not consistent by its normal discharge currents. It can be low as 2,000 amps to well over 400,000 amps. Average around 30,000 amps. So if we have to be 100 Ka, 5 strikes out of 100 are 100 Ka and greater. So it's pretty, 5% of our strikes only get to 100,000 amps or greater. They're pretty rare. But if you had a high lightning current strike with a fast rise time, you run that equation, you can develop a pretty significant EMP. And as in this scenario here, we're showing you a building that has developed the upward streamer. These lightning rods have done their job. They've captured the lightning strike. They're taking it down structural steel, building steel to ground. And as that energy flows, that current flows down that building steel, it develops that electromagnetic pulse, EMP, that radiates through the air and gets picked up on all of our intra-building sensitive computer systems, maybe a power distribution, maybe our data, communication, phone lines, all have that energy reflected on it, and now we have damage. So again, a quick review here. These are some of our major problems when it comes to secondary effects, creating problems with our operating systems. I would add another one down the road, especially in today's oil and gas environment, and Sean will talk about that later on today, is that there is an explosion event too that's not drawn out here in dealing with some of our unique challenges we have now in our oil and gas industry in the United States. A quick summary of some of our secondary effects of a lightning strike as far as characteristics. Our peak current in lightning could be 2,000. I mean, the highest recorded, at least recorded, 500,000 plus. Extremely rare, extremely rare. Most of the strikes you can see are under 200,000 amps. But again, 5% of those strikes really exceed 100,000 amps. Most of the strikes right around 30,000 amps or less. So if you plotted 100 lightning strikes on a curve, you'd have the vast majority of lightning strikes between 10,000 amps and 50,000 amps. Probably 80 of the lightning strikes out of 100 would be between 10 and 50. The other 20 would be below 10,000 amps and above 50,000 amps. And it's a high frequency. I'll always like to point out the fact that lightning is a high frequency. Even though we're talking about positive and negative, when it discharges, it oscillates. So if you have a high inductance path for that current flow of a lightning strike, even though it might look like it's very low resistance DC, if it has an inductive reactance to it, it's a high resistance to that frequency, and it won't be the preferred discharge path. So any kind of a discharge path you have, you want to make sure that it's a low inductance path. Okay, in the United States, and I'm sure some of you have the same challenges that we might have, we have our standards group. Here are the two that we mostly see in the States. National Fire Protection Agency 780. We do have a seat on that committee. In fact, Luke does all that grunt work on the 780 committee, so Luke is on this committee standard. They're all geared to lightning rods. That's their mission. the bottom line is they are collectors. They've been around since Ben Franklin. We'll talk about that later. And they are traction systems. The downside about this is that a lot of companies that we work with, well, probably a lot of the engineering firms we work with, and some of the companies say, well, is it a standard system? And the answer to our dissipation array system is not a standard system. The SPT and the SPI have been a standard system, and at least our standard system right now. Well, who developed that approach? Now, I'm sure all your countries have similar, either British standards or what have you, but they all kind of go back to this guy right here, Ben Franklin. He's the inventor of the lightning rod. Around 1750-ish is when he actually invented the lightning rod approach. Pretty impressive when you think about the fact that was 1750s, no voltmeters, no current meters, no oscilloscopes, no instrumentation, all basically him thinking in our mind about what creates these charge separations and so on. He actually thought about a sharp point dissipates a charge, which he was correct on. Again, there's no way he could have known that or tested that. He had no instrumentation. But he did come up with that analysis that a sharp point will bleed off a charge. He linked lightning to a charge. Again, not too bad for a guy who had no experience, self-taught for the most part, entrepreneur, and also a politician and maybe a bit of a womanizer too at the same time. And lightning rods initially were an attempt to actually actually dissipate a cloud. He thought, if I put a sharp point on my barn, I can bleed off that charge. Well, quickly found out that it did the opposite. It was a collector. But from a reality standpoint, back in the 1750s, 1800s, there were no instrumentation, there were no computers, there were no sophisticated DCSs, PLCs, all the things that we use now in our normal operations and our sophisticated operating industrial systems. That worked fine. The main goal that he had back in 200 and plus years ago was, 50 years ago, was protecting my livestock, my goods, my house. That was what they had to worry about, because that was their life to them, their houses, their barn, their cows, and their grain, their goods. And it did a very good job in that. But in today's circumstances, it's really not the right choice. Obviously, it didn't sufficiently dissipate the storm cell, did protect the structure from fire, was the preferred termination point, and basically was the beginning of the evolution of the standards we use now. So Ben Franklin is the father of our conventional wisdom in lightning protection. In fact, it's still called in many circles the Franklin system. Now here's some examples of, well, here's a lightning rod right here, and these are different type of collectors dissipators. But that's the Ben Franklin product right there. ESC device, you may hear of an early streamer emitter. An early streamer emitter is you might recall when I talked about a strike zone, what's in a strike zone, or that slide I did about 15 slides ago with the yellow colored cone envelope, or sphere envelope, I should say. That has a specific collection zone based on certain parameters. And ESC basically says, I'm going to put one of these devices on my building. I don't need to worry about having a matrix of 100 lightning rods on this building or 20 lightning rods, whatever the standard says. It's all based on a standard and spacing. For example, on the perimeter of a building, you would need spacing of 20 or 25 feet on the perimeter. So the bigger your building, the more lightning rods you need. You need a certain amount down the middle, 50-foot spacing in the middle, 50-foot spacing between rows for a conventional design. Whereas a ESC says, hey, I can just use one of these and I'll collect everything within 60 meters. Let's say 120 feet or whatever it might be. I'm going to collect. Well, reality is, or 90 feet. Reality is, there's been some controversy there. We don't get into the whole, do they work, don't they work? We don't really sell against it. We do come up with ESCs on occasion. We don't really debate whether they work or not. Personally, I say they work all the time, because do you really want to collect every lightning strike within 100 meters that might hit 100 meters away and bring it into your property? Probably not a good idea. This just shows an example of some of these devices that are made peak out about 100,000 amps. Anything over 100,000 amps, you can burn the triaxial cable. And that's just what happened. There was too high of a lightning strike current which damaged that ESC. Lightning rods don't always ensure collection. Here's a lightning rod on a pole, lightning hit right here, probably a sliver of wood, developed that streamer, and so even lightning rods aren't 100%. The consensus that I've gotten from the manufacturers, or when I was sitting on the committee before Luke took over, was that, yeah, it's debate between scientists about is it 90% or 98%, but probably somewhere between 98% effective collecting all strikes and 90% is your conventional lightning protection design. Now, I like to show a slide here for a couple of reasons. One is you can see what a lightning strike can do as far as an explosive event. That was a lightning triggered event at a storage tank in Kansas City about 5+ years ago. I also like to show this because look at this lightning bolt here. It's a pretty good example of what we can see in a typical lightning strike and the wide area of influence this lightning strike has to being collected. That's that tank after burned out. That's a tank on fire. That's like 5 days later. And it was about a $10 million loss to that particular end user. It was about a $3 million loss. It was completely full of unleaded gas. So they had, and by the way, once it's on fire, what do? Nothing. I mean, as far as putting it out. You put water, the fire department shows up and puts water on that tank. And puts water on the other tank to keep it cool, but there's no firefighting. It's damage control. Let's let it burn out. It took about 2 or 3 days to completely burn out. And it basically burned off all the fuel. That's what they did. So after the tank completely burned out, then you had to clean up. And then we had issues with the cleanup cost and all the costs of a new tank, the cleanup cost, and the bad press that company had, because everybody in Kansas City could see that for about a day in the nighttime. It was a pretty big luminous fire. And so bad press is not a good thing either. And here's an example of a lightning strike explosive event at a gas process facility in Florida about 10 years ago. But you can see the damage that lightning did, creating a fire explosion at this process facility. That truck was parked some distance away, and just the heat from that fire totally damaged that truck that was sitting about 100 feet plus away from the fire. So in review, when we talk about lightning, we've kind of laid the foundation here for a lightning event, for what causes lightning, part of the discharge process, part of the secondary effects caused by lightning. We've laid that foundation out so we can get a good understanding of what can occur during lightning and what creates the discharge process. And what we were able to ascertain was that obviously lightning is a significant event. It caused tremendous damage either by direct strike, explosions, or secondary effects. And really the principle we're trying to lay out here is why would you even want to attract lightning? Because lightning itself creates a lot of potential problems. But the conventional wisdom, going back to Ben Franklin, has always been, let's collect. Let's actually be proactive in collection. And we're sitting back here saying with all of our, as a company, with all of our sophisticated electronics we have now, and the potential for explosion, why would you want to collect? Why would you create an environment that actually tries to attract lightning? And that's really kind of what launched our company into a proactive mode of lightning protection. The company, probably most of you know, some of you may not know, the company was originally founded in 1971. So when you think about it, we've been around for a long time, 44 plus years right now, in our 44th year of business. Really with the principle of taking a different look at lightning protection. Again, going back to the late 60s, there was only one approach in lightning protection. It was using that 1750, 200-year-old technology approach, Ben Franklin. And as many of you might know, the founder, my dad, who actually worked on the Apollo project, was charged with reliability analysis for the Apollo program, did research on, when you're a reliability engineer, you look at everything. What can impact reliability of my particular product, or in this case, that launch vehicle's mission to the moon? And what he found out was that there really had not been any true innovation, improvement in lightning protection since Ben Franklin. And when you think about this is, you know, when the United States is in the space race trying to get a man on the moon, trying to beat the Russians to the moon, and yet we're looking at trying to do that very sophisticated, aggressive, high-tech program, yet what we're going to protect our launch vehicle is a Ben Franklin 200-year-old technology. So I'm thinking, that doesn't sound right. Something, you know, we've got all this great new sophistication, computers, instrumentation, rocket technology, navigational technology, yet we're using 200-year-old technology for protection, and we got basically, all I can describe that as, you've got a person, you got 2 or 3 men sitting on a stick of dynamite, and you're hoping it doesn't blow up. And you're going to protect them from a lightning strike with a Ben Franklin technology. And that's what had him, launched him on his own little mission to look at unique introductions and ways in developing a proactive lightning protection system. And that's what really got us into the dissipation array technology. This is I like to refer to it as the lightning rods react to a lightning strike in the area concerned. It develops an upward streamer. So it's a reactive system from that standpoint. We are a proactive system. What do I mean by proactive? Rather than waiting till lightning leader's already been developed, I want to be working on the front end of the curve, on the initial storm generation. As lightning starts to move into my area, I want to actually be proactive in creating an environment that's not conducive to lightning collection. And that's really what the dissipation array is, a proactive technology, working before the lightning event and during the lightning event to not collect lightning. As I mentioned, the technology was first came into being in 1971, been in 44 years. I like to describe it as, you know, people say, I've never heard of this technology. Well, it's true. We're still trying to get the word out. We're still trying to, you know, preach the gospel of this technology. But we are older than Microsoft. When you think about that, so we've been around longer than Microsoft or other companies that are quite large. So we are actually, when you think about it, 44-year-old technology. We've been around. We've gone through a lot of development, a lot of improvements, a lot of testing case studies that we'll talk about later on. So even though some people might say, well, this is a unique, controversial technology, been around for 44 years. We have a tremendous amount of history in the field proving this technology works. Well over 30,000 systems worldwide, and with our dissipation array system, just that particular version, not our spline balls, we do offer a no-strike warranty, functional guarantee, not an insurance policy, but a performance guarantee. Let's talk about the basic principle of this technology. Lightning is a discharge. We're talking about transferring a tremendous amount of energy, 10,000 amps, 20,000 amps, 30, 50, 100,000 amps or greater in microseconds. Well, the dissipation array, or our ionizers, whether it be spline ball or otherwise, is a charge transfer system. We generically call it a CTS, charge transfer system. But rather discharging that in microseconds, we're going to create a continual, constant discharging during the course of the storm. So we're doing discharge over time. An average storm cell area lasts about 20 minutes. Now granted, you could have a couple storms go through where you might have maybe an hour of storms going through because there's different cells. But typically a storm cell lasts about 20 minutes. So you're discharging that site during the course of that 20, 30-minute time frame. What's the approach we're going to use? What's the technology we're going to use? What's the methodology we're going to use? Well, really since the early 1900s, scientists have known, engineers have known about a natural process called point discharge. Point discharge is a simple, natural phenomena, and you can easily replicate that. Do this yourself in your backyard. You could prove point discharge in your own backyard, as long as you have an electrical storm in the area. You can't do it on a clear day. But if you had the inclination to get, let's say, a nail and get an analog, not a digital, an analog needle current meter, the current meter has to be actually operating, working, because you can't get many needle meters anymore. But if you have maybe your old electrical surplus house, that we used to use, and you always go to these old electronic houses, they'd buy old equipment. You might be able to find an analog current meter, let's say 1 microamp full scale. You don't want to have too much, you don't have too much attenuation. You want to have like 1 microamp full scale, because you're only going to use one nail, 1 point, put it on a wooden pole, run it through that analog current meter and ground it, put a ground rod in, and have it maybe 5-6 feet in the air. And as a storm moves in, you're going to see that needle deflect. It's going to actually show that you're bleeding off current. So you can easily do that on your own, but the key is get an analog current meter, make sure full scale is about 1 microamp, because you're only doing like one nail. You're doing a very simple test. But you can prove that. You can do it for your kids for a homeschool project or science project. You could do that. Taking a picture of the actual needle deflecting, taking a video of it. It's easy to replicate. Remember I talked about we're a passive system? We talked about being a passive system, but what makes it active? We use the storm's electric field as a motivating force. We are a grounded system. There's no power supply. It's a ground potential. It's not going to shock you, but it is active. It bleeds off current caused by the storm's electric field. And we do know that during a mature storm, electrical storm, there is a very high electrostatic field developed, at least 5,000 volts per meter, up to 30,000 volts per meter. And remember, that's per meter, per air. So obviously, if we start at ground level, let's say 10 kV per meter. Let's see my storm that we're working in right now, that electrical storm has 10,000 volts per meter of charge in the air. So keeping it simple, making it linear, you have 10 kV for the first meter, 20 kV for 2 meters, 3 meters. So my ionizer, my dissipator, is usually at least 30, 40 feet in the air. Sometimes it's even much greater. So the potential on that ionizer is significantly greater as you get higher, which actually drives up the current flow even more. Now, we use that point discharge as a motivating force. Now, it's important to understand that to develop and optimize, and for lack of a better term, calibrate this system, the basic design criteria is critical to achieving maximum ionization current. What impacts how efficient my ionizer, my dissipator will be? Point spacing. So how do we make an ionizer? How do we make a dissipation array? Do we just throw those points up there and hope it works? No, we've been around for 44 years, and over that course of 44 years, there was a lot of field testing, lab testing to develop the most efficient ionizer. And it's based on point space, point length, and number of points. So going back about 20 years ago, we did a major test program in Boulder where we literally tested hundreds of test samples in our electrostatic simulator with different length and spacing between points. And we basically energized our simulator starting at 1 kilovolt per meter, went all the way up to over 30 kV per meter. And we plotted on a curve the current flow at each point in the spectrum, 1 kV, 2 kV, for all our test samples. And also we compared all those samples, and from it derived, and with some modification of samples, derived the most optimum efficient ionization device for our dissipation array. And then we basically said, okay, what can we do for a lower cost version that's a hybrid? That's where this blind balls came in. Not as efficient, but lower cost and provide a tremendous amount of ionization. So this is what we have right here as an example of one of our simulators that we did back really 20 plus years ago. We no longer have us in place right now because we had to take down that area and use it for our lab area. So this is no longer available, unfortunately, but it did provide all of our testing for that confirmation of optimized ionizer. So here's our top plate, signifying the bottom portion of the thunder cell, our insulators, and the bottom plate is the earth, top plate the bottom of the cloud. We put our test samples in there, we activated the simulator, and if you've heard of St. Elmo's fire, St. Elmo's fire is a natural dissipation. It's actually a natural corona. It's a glowing effect caused by a high charge in the air and bleeding off a charge off of either a sail or a tree, and that is a form of ionization, really. But this is really showing you a enhanced, effective, fine-tuned ionization. So when you see the simulator and you see the example of this active system, you can actually hear the corona. It's kind of like bacon sizzling. You can smell the corona, and you can actually see the current being bled off of the ionizer. Now, if we were, let's say this was about 20,000 volts between the bottom plate, top plate, pardon me, and the bottom plate, and I was to activate that at 20 kV, you'd see the ionization effect of glowing off the ionizer. We were to pull out that sample and put one lightning rod in there and start at like 2 or 3 kilovolts. By about 5-10 kV per meter, we're showing a lightning discharge on the one lightning rod at a much lower potential, showing that really a lightning rod actually is going to initiate a strike, but this is really tempering, preventing collection, actual termination. Here's an example of an active system. That's actually one of our dissipation arrays showing you a corona cloud from a security monitor. It's very grainy because it's one snapshot of a video camera, but you get an idea of the corona cloud. So I've got a few examples here I'm going to show you. Our newer slides and our older slides, because I think working together help kind of get this point across. So now, when we go to, and this first example is based on, let's say, a refinery or power plant. So here we have our stack. A lot of times, in this particular case, let's just say that the real concern of this particular client was his environmental monitoring systems on his stack. The EPA says, hey, you've got to constantly monitor your emissions on that stack. We're going to, I'm sure a lot of you have heard, and it's happening in some of your countries, that we have a very significant, aggressive greenhouse gas issue, trying to minimize our emissions, to minimize greenhouse effect, loss of the ozone, cleaner environment. So we're being very aggressive in the United States about that, about lowering our emissions. We're very aggressive on coal burning here, cleaning up coal to where it's going to burn cleaner, for example. But whether it be any kind of emission we're putting out of the stack, whether it be basically a coal byproduct or gas, we have to monitor the emissions. The EPA, our Environmental Protection Agency, very aggressive, extremely aggressive right now, comes out to a plant and says, okay, you can only allow so much emissions out of the stack. Anything over that, you're going to get fined. And so you have to constantly monitor the emissions 24 hours a day and record that and report that. So if this environmental monitoring system that's on the top of the stack and also is housed in these little buildings here, if it gets damaged, then the EPA comes in and says, okay, I'm going to basically say you're putting out the maximum emissions because you're not monitoring it. They're thinking maybe the company pulled a fast one. Oh, I broke down. Okay, fine, you broke down. You're going to be examined as you're putting out the maximum emissions out of that for the time you're down. And if they go over, they get fined. Plus, these can cost $50,000 or more. So you have the cost and you have the concern of the downtime. So this example here, this particular client said, all I'm really worried about is my EMS system. Everything else, that's my only lightning vulnerability I'm worried about. Okay, with that said, we're going to concentrate our protection for just the stack EMS system and the instrument housed in the rooms. That's our mission. That's our goal. We're not worried about lightning around here. So with that foundation laid, we decided to put based on the application, a stack array on this stack. That stack array develops a zone of protection. We get asked that question all the time. What's your zone of protection? What's my protected area? Well, it's based on a few variables. What's the height of what my ionizer's on? What's that height? We have a max height limit, but let's say anything up to about 300 feet gives you an envelope of about 300 plus protection zone. In simple terms, the most simple terms, height equals radius, up to about 300 feet. But it's also kind of a hemisphere versus a zone of, your typical zone of protection is more of a 45-degree angle. This is more of a hemisphere. So everything in this zone right here we're saying will not collect a strike. We can do envelope protection drawings for engineering too. If you want that, usually a little extra cost. If you want to have the hemispheres drawn and the zone protection drawings, a little more engineering time, a little extra cost. We can do it. Some of my clients have asked for envelope drawings. So now here's our protected zone caused by, so in this particular case, all we needed to do was install one hemisphere dissipation array, ground it, make sure it's all calmly tied together, and now we're protecting all the client's area concern. Again, we're concentrating on this area here. So now let's kind of go into the whole process here. So now we have our lightning storm coming in. Now I haven't shown the positive charge up on the cell, the negative charge here. It gets a little busy as far as graphics, but you see it's kind of this little glow right here, this little gray cloud. What that is basically our corona cloud. We call that a space charge. So what's happening now is the storms within the area, we're grounded, our points, our multi-point ionizer is immersed in that high electrostatic field as the storm grows. So as the cloud comes in, as the storm moves into the area, the electrostatic fields grow slowly over time, and we start to bleed off that charge. We're letting electron flow. Now we're talking about, remember, electrons, not enough over here, too much over here. I got too many protons down here. I need to have a free flow of electrons, slowly and controlled electron flow, methodical flow, to neutralize that charge. So I'm kind of slowly, continually allowing a free flow of electrons from one area that doesn't have, has too many, to one that doesn't have enough, to neutralize that charge. And when I neutralize that charge, I've created a, we're going to call it a space charge, a corona cloud. And that's that gray area here. What this really is signifying is a very low electrostatic field in the area concerned in relationship to the surrounding environment. For example, we might have 5,000 volts a meter here, 25,000 volts out here. Why? Because we bled off that charge. We've neutralized it. We've allowed that flow of electrons slowly, continually, during that 20-minute cycle. We're constantly bleeding that charge off, lowering the fields, keeping the fields low. Why is that important? Because now we have a lightning strike developed in the area. We have that lightning leader in the area. It's coming down from the cloud, and it's, remember we showed you those big branch circuits? It's looking for an area to be collected. By the way, it might be, I didn't talk about this, there's three types of electrical discharges. Intercloud, where you see the cloud light up, you know, discharge between the positive and negative, well, we don't care about those. Cloud to cloud, you see that lightning bolt go across the horizon and terminate the adjacent cloud. Cloud to cloud. Now, there is potential for current flow along the earth for a cloud to cloud strike, pretty minimal. But this discharge, it could go cloud to cloud. But this case here, this coming down, heading down towards the earth. What's going to happen now? We've created this space charge. What happens? There's three things we don't want to have happen to our system, or our protected zone. We don't want to have upward generated lightning, upward leader. We talked about that. Well, if this is a 100-meter tall stack, it could do it. Remember I said that anything over 100 meters theoretically could develop upward lightning. Well, if I keep this potential so low, below the threshold of lightning, I'll never develop it. So I keep those fields below that of lightning, ground developed lightning. Pretty rare, that's a pretty rare one. But as that lightning bolt comes down, let's just say part of that branch is heading towards my stack. What happens is because the field intensity here is so low, as that leader approaches that area where that space charge is, it actually slows down. It slows the speed of that lightning termination. We don't need to slow it down much because the field intensity here is maybe 5 kV per meter versus 25 kV out here. It tempers that speed, and that's all we need to have in one of these series of operations to ensure that lightning then is going to be one to the other area concern. So backing up here again, if we have a leader heading right for my protected zone, when it hits that space charge, it slows down. We're only talking a few milliseconds. We don't need much time, which is just enough time for his other branch to seek out and be collected by another streamer some distance away. We don't care if that lightning leader is 100 meters away or a mile away. We just want to make sure that we don't two things we don't want to do. We don't want to have that branch get into my area to where I develop an upward streamer. We know that we have to have an upward streamer to win collection. And in order to win collection, we have to have, in order to develop an upward streamer, the electrostatic field potential, I don't think I touched base on this, very important, has to be 100,000 volts a meter, approximately. So for this area here, to develop an upward streamer, the electrostatic fields have to be around 100 kV. If I slow that leader down when it hits that space charge and I keep the field intensity in this area well below 100 kV, I will never develop an upward streamer. And if I never develop an upward streamer, I'll never collect. That allows some streamer off-site, and it could be a mile away, a kilometer away, because you saw that lightning bolt we showed you, how far that area influence is, to win that race. And by not winning that race, we'll never have collection, and we'll never have secondary effects. Next slide here, we're showing you the example of the discharge after the strike. So here's another example. I'm going to throw this one in here as a different visual aid. First of all, I hate this slide because it's got a very big array. Not a good example. But what I like about this is these squiggly lines here, this is showing you a very high electrostatic field. So these dark lines are showing you that outside the area of protection, the electrostatic fields could be 25 kV, 30 kV, high potential. But because we've discharged the site slowly and continually by a ionizing technology, multi-point ionizing technology, where we're constantly bleeding off that site slowly, methodically, continually during the course of storm, we don't allow a very high electrostatic field around our zone. And by doing so, when that lightning occurs, we'll never generate the upper streamer. Why? You have to have 100 kV per meter. We're way below that. And we're slowing that leader down because it hits a space charge, it slows down, then allowing the lightning to be collected off-site. So when we talk about this technology, our dissipation ray system, our company name is Lightning Eliminators and Consultants. The elimination part may be a bit of a misnomer. We're not eliminating lightning from occurring. It's going to happen intercloud, cloud to cloud, cloud to earth. We don't care. We just want to make sure that it doesn't hit our protected zone, that we're not going to be a component for collection. We're not going to allow the recipe, the environment to be a collection area. And that's our whole principle. Any questions on that part? By the way, one thing and we'll talk about this afternoon, we have just developed and scrubbed down, myself, Lee, Joe, Darwin, Luke, has spent about 6 months on and off going through all of our technical papers, at least the ones that we use a lot. And we have updated with your terminology, new data we have, all of our technical papers that reflect everything we're saying here and more. So I just want to give you a heads up. You're going to have a discussion later on, but don't feel like you have to go ahead and retain all this right now. You'll be able to review that at your leisure or review the video. But what we're really doing is, simply, we're creating an electrostatic environment by a proactive multi-point ionizer that's been fine-tuned, enhanced, calibrated to get maximum efficiency to create an environment that's not going to collect. And by doing so, we prevent all the secondary effects and ensure maximum reliability for that system operation. Now, I've got just a few minutes left here, just a few slides left. When we go back to this slide here, I'll go back to here if I can. This is our protected zone right here, right? We're not going to have any lightning collection in the zone. But if we had an AC power line coming in from outside into this building here, which you always typically do have, that still was a point of vulnerability. We could have a lightning strike off-site to a transformer and come into the power side. So you want to make sure that you also then look at all the points of vulnerability to a lightning strike. We can protect and prevent a direct strike, but if they have a low voltage line going out to a remote instrument that exits that zone, it needs to consider proper lightning protection from a surge protection standpoint. And Brian will talk about that later on tomorrow morning. Hopefully you're all awake for that one. It's always a fun one for Brian. But you can see here we're saying, okay, hey, we prevented against a direct strike. We have a dissipation array on our building here. But we also have to make sure we isolate the distribution panel, and maybe we'll use our TLX100 for a distribution panel. At the main entrance, we may want to use a facility guard. So when you look at a facility, we want to look at a lightning protection approach as we're having 3 legs of a stool. A lightning protection system should have 3 legs of a stool as far as its protection components. Direct strike, 1 leg. Dissipation array, spline belt ionizers, match that, provide that direct strike protection. Secondly, surge protection. I like to call it strategic surge protection. Any vulnerable power line that enters that facility should have a strategic surge protection. Sometimes they already have them on site. Very common in the United States side. So we'll maybe get to the site and they've already got surge protection. Okay, as long as it's a good product and there's plenty of them out there, then we can say, okay, that's protected. Then thirdly is a grounding. So this, make sure we look at a site, have we looked at all of the points of vulnerability that feed that protected zone, that penetrate that protected zone? Would it be low voltage or AC power? Because if we don't address those, and they have a lightning strike in the vicinity, and it comes through what I call the back door, they're going to say your system didn't work. Well, those are going to be isolated too. Now, if they want to assume that risk, as long as we're upfront and saying you understand that these lines are vulnerable, then that's their call. We have low voltage too. So whether it be our TLX lines, which Brian will talk about surge protection, or our DLPs, we have a complete line of AC power, low voltage protection, whether it be for fire alarms, coax for security cameras, analog circuits, digital circuits. We have a complete line of protection we can offer to get a systems approach. Systems approach meaning you've taken a look at the direct strike, low voltage, AC power, and here's some of those products right there for the low voltage side, whether it be our facility guard, DC power supply protection, DIN rail low voltage protection for analog digital circuits, coaxial protection, data line, landlines, Ethernet. We have all that protection. Pretty much, I think we probably have 95% of the potential applications covered with protection we have as far as low voltage protection or AC power protection in our system. We also have medium voltage. We do up to about almost 5,000 volts AC for pumps and so on. Most of those come into play in the oil and gas industry. And of course the chem rod, and there'll be discussion about chem rods later on. I won't go into a lot of that discussion, but what we like to say is from LAC standpoint is that we offer truly a systems approach. Systems meaning we look at all points of vulnerability. We pride ourselves on being the company that can provide all the expertise, the engineering consulting, the design, PEs on staff, the sales support, consulting work, integration. We actually even do turnkeys once in a while. Prefer not to do a turnkey job, but Brian's got one right now that he's sold for $500,000 on a turnkey job, where we're doing the installation, everything. So it's a pretty good sized contract that in this particular case, the customer wanted to make sure they went through us, and unfortunately we agreed to do that. Well, on the upside is we're not going to make money on it, but we do turnkeys on occasion. Depending on the application, we will do that. Where we can take all this together and give system certification. And again, we want to have a good low impedance common grounding practices. So when we look at a site, are they using good grounding practices? Is everything bonded, tied, commonly together? So the grounding system is working as a team, and is it achieving a low resistance ground? The standards don't address that. We believe that you do want to have a low earth contact. I like to tell my clients, especially for a guaranteed system, we want a 5 ohm or less ground. And most times it's very easy to get, especially with the chem rods. Now in Louisiana, not much, if you're down in New Orleans or Lafayette, you just dig a hole, you get a good ground. So obviously it depends on your location. West Texas, Dallas, you got a problem with ground. Beaumont, Houston area, the Beaumont Ship Channel area, not too bad because your soil is so conductive. And we'll talk about that later on too. And just a quick example, we're almost done here. Carl's here, one of his, as Brian likes to call it, his cash cow, Federal Express, has been a very good customer of ours over the last, what, 25 years, at least 30 years, I'd say. And Carl and I have been working on that with that account for, I don't know how many years we've known each other. 20 years now, Carl? 25 years? Oh, geez. So we've been working with Federal Express, a very good client. We've every year have business with Federal Express, either mostly at the super hub, the main hub, but also we've done work in Colorado Springs, Newark, and some other locations for Federal Express. We have really over, last I heard, it was over, what, 230 gates or something like that, the gates. So we have over 230 hemispheres at the Memphis hub. In fact, I was just talking with somebody yesterday morning who wants to protect the heliport for all the offshore heliports in Louisiana. Well, talking about it. He knows, hey, I know I've seen you at Federal Express. Well, it didn't hurt our application because he knows about Federal Express. And if you fly into Memphis, the FedEx airport is bigger than the commercial airport. Pretty extensive. That's one example. Tank protection, done a work in Lagavon, Venezuela, U.S. We had a couple nice jobs in the U.S. this year, where Sean and I worked on with EOG in Texas, four tank arrays to a tune of about, I think it was about 50, 60 grand for 4 tank arrays in Houston. Good application for tank arrays with the EOG resources. It was a nice order. Those, we can do those. Data centers as an appropriate application. Anything, we've even done homes. Now, Kirk's not here right now, so I can say that without getting him too upset. We've done high dollar ticket homes. We don't like to do them because typically there's not a lot of margin in them and it's difficult to do. But if it's $1 million home and they want to invest $20,000, $30,000, we have done multi-million-dollar homes. But reality is that's not our forte. Our forte is heavy, I call heavy industrial applications. Power plants, chemical plants, oil terminal facilities, process facilities, communication sites, data centers. That's really our forte. NASA, this goes back many, many years, 30 plus years, down in White Sands in New Mexico, a hemisphere array right there. I just threw a few slides in here. One of Brian's accounts that's still buying from us is PPG in Lake Charles. They still have applications they're working on even today. Axial, now they changed it to Axial? Okay. And if you've heard of CNN, even around the world you might have CNN, we protect their main corporate hub in Atlanta, which they're based out of, with our technology. Been doing that for many, many years. And Brian had a couple jobs last year with them, didn't you? Every year with CNN, so, and Turner, which is their corporate company. Offshore platforms, work on them. So stack arrays, paper mills, power plants. Obviously, example of our stack array on a, I think it actually is a power plant. And I didn't throw many slides in because we had a lot of information in a rather short period of time. I think I'm just on time here, 5 minutes early. Any questions at all? I'll be around for a while. I will say this again, and we'll talk about it briefly this afternoon or tomorrow. We have just scrubbed down all of our major technical papers. Will be lightning protection, secondary effects, hybrid lightning protection technology, and what am I missing? Grounding products, and tank mitigation. So this last year, one of the things we did do on the technical side was really take a proactive approach with a committee of about 5 individuals to really get those papers up to date. So I suggest that you always make sure you have copies of them and use them obviously for your own use, but also for your customers' use. And we appreciate the opportunity at least to get that out to you, and please use it as a tool going forward.